Hi everyone. So after we took a look at the kind of refresher on Python, I wanted to introduce object-oriented programming. Some of us may have done this before, but this book gives us a pretty large overview of the purpose of it. Before we go into the specific coding, I just wanted to use some key terms that you'll be looking at. The quizzes might ask about these, so just have the PowerPoint handy. But essentially, what a software engineering problem looks like and how we can approach it. So object oriented programming serves a purpose, and it's to design software or an application that is robust, adaptable, and reusable. Now, we could think about this as the application as a whole or specific parts of it, but essentially, robustness is where a user might do something unpredictable, so your code needs to respond to that. Is adaptable, so if there's a new release of software or a new hardware comes out, it can be useful for it and reusable. So essentially, if you have a similar problem with a few different things changed, you could reuse most of your code. So if you keep these three ideas in the back of your head while you're coding, you're going to create much more effective applications in the future that you could reuse going forward. Okay. Now, there's some principles that I'll break down to us that come with object-oriented programming. Again, some of these names, it might be confusing to balance some of these names because of the syntax, such as modularity, but we'll use these key terms and then go from there. So modularity essentially tells us that the piece is comprised a whole. So each part of the code is a modular part that built together creates something. So again, you can think of a house as electrical, heating, structural, and plumbing modules. When you put those together, it creates a house. Now, this is useful because you could probably apply the heating and electrical to a different area, and maybe it makes an apartment or a garage. You could also think of this as a set of Lego, right? Each little part of the Lego you put together creates a new object. Abstraction is a bit more difficult, but it's essentially you're going to distill a system into its fundamental parts. So essentially, what you're trying to look at is you have a problem and you're trying to get to the basic parts of that problem and then build up from there. Abstraction is going to coincide with our abstract data types, which are mathematical models of a data structure, and that includes the data that we're working with, the type of operations we can do at it, the types that are inside of that data, and the parameters passed between it. What this pretty much means is what the data is as an ADT, but it's not going to tell us how we could work on it. That's up to us to decide. Now, one more thing with abstraction is that Python can provide an abstract base class that's going to define methods that all concrete classes that use the abstract base class must implement. Now, this sounds kind of confusing, but you could think of it as car ABC, and then you could think of it as like a Toyota concrete class or a Nissan concrete class or whatever other car you want to use there, right? So your car is your abstract base class, and your concrete classes are Toyota, Nissan, and stuff like that. So essentially, you're going to be implementing the concretes based on the off this one. But let's just see what's something that's here. Well, all cars should be able to drive. They should all be able to brake, and they should all have four wheels, give or take, right? So those are kind of your ideas there. Now, encapsulation is the final component or principle we're looking at. And encapsulation means that different components of the system don't need to reveal the internal details. The book does a good job capturing this, right? You have a light switch covering all the stuff that goes on in the background, but you can think of this as a drive-through as well, right? When you go up to like a drive-through and you ask for food and you put in your order, you don't actually know every single thing going on in the back end, like if who's cooking, when it's done cooking. All you know is that you enter in, you place your order, and eventually it comes out to you. So all that stuff that's going on inside is encapsulated. It's hidden from you, and you only have so much information visible to you to use, right? And this makes sense if we think about if we think about Twitter or Facebook or YouTube. You just click on an image on YouTube to go to a video. You don't really know what's going on in the back end to get that video to you. All you know is that when you click it, it should respond to that. Okay. Cool. So design patterns are its own class. They're its own beast essentially, and we're going to be looking at what these are in context of algorithmic design and software engineering. More so a focus in this class on algorithm design. Software engineering could be its own monster later on, but essentially, what design patterns are solutions to typical software problems that you're going to encounter. So what this means is that throughout our kind of small history of computer science so far, there's been issues in software we ran into. So issues are abstracted into the main elements, and these main elements are solved using a specific type of approach, and then the programmer can apply the specific issues here, right? So in general, what this means is that it's a general template for a solution. Okay, so you go up to a design pattern guy and you say, okay, I'm trying to design this application where a user enters in their information and then a score is created. So they might supply a specific design pattern to use for that, right? Now, of course, in our experiences here in this class will be more bare bones, but you can think of there's a few different ones out there. There's a factory method that we have down here, which is similar to what we have over here. The car is the factory and it produces different types of cars. There's an air controller method where an air control tower essentially is in control of all the other actors. So a lot of these things are kind of analogies or different types of things we see in real life, but we apply them to our main issue. Let me change this to focus. Sorry, I misspoke there. Cool. So the categories that we have here are algorithmic design, algorithm design, and software engineering design. These are ones that you're most likely not familiar with yet, but have seen or heard of. Recursion is our first one. Amortization, divide and conquer, prune and search, brute force, dynamic programming, and greedy method. Okay. So we'll for sure try to cover all these. For our software engineering design, we're going to be looking at iterators, adapters, positions, composition, template, locator, and factory method. There's much more than this in software engineering, but that could be its own class. But essentially, we're going to for sure try to get all of these, and these are going to be kind of sprinkled in throughout it. But the focus of this class is on our data structures. Okay. Great. Now, finally, we have our life cycles, and essentially, what your software needs to be aware of when you're creating a piece of software is what are the responsibilities associated with that software, what is the independence of that software, and what are the behaviors of your software. So you can kind of think of this as, uh, let's just say that you're trying to organize work and you have a group of people with you. You could think of each person as a class, and we'll talk about making classes when we start programming next. But you need to figure out who is responsible for what in your program. You need to figure out what work each person is going to be doing and how those people communicate with each other. So, who has autonomy, who doesn't, who passes the data, who does what, and the behaviors. Now, behaviors are important and they're going to be changing as you develop your software, but you should try to have a bare bones of what's going to be going on for it. So, you want to make sure your functionality is maintained using behaviors, and essentially behaviors are what will interface with others. And so essentially a drive-through has an actor in the drive-through, such as the person taking your order, has a behavior of speak or take order, and that's going to interface with me, right? So these behaviors are going to be what other people or coders are going to be looking at. So, one more few things here. Always make sure you comment. It's a pound sign inside of Python. The more comments, the better. It's a friendly reminder to yourself where you are and for others who might be reading the code. And then also create test scenarios for special cases such as null errors or empty lists. Great.